One more. Since we started Wednesday by talking about ideas calculus is derived from in geometry, really calculus was developed to understand two geometry problems. The first of which is called the tangent or the subtangent problem. If I give you a curve and a point on that curve, I would like you to create a line that only touches the curve at one point, that point. Now, if I'm willing to be sloppy about it, I could ad-lib this, and I could take a straight edge, and I could kind of go back and forth and say, well, all right, maybe that line, draw it on there with a pencil, right? But how do I construct such a line? In geometry terms, back in classical Greek geometry, there were only two tools you were allowed to use: a straight edge to draw a line, and a compass, the kind with a point and to measure arcs and to draw pieces of circles. We have algebra tools though. So I'm going to take this curve and I'm going to put it on a set of axes. And we'll call it a function f of x. And now I can say I have some x value, and therefore this point has an x value and a y value. And I want a line. I have a point. What's the other thing I need to make a line? A slope. So really this question just changed. And instead of asking, how do I construct the line, I can ask how I find the slope of the line that should go through this point. I'm going to make, again, that sort of half-assed sketch here. That's the line I'm after. We'll call it LT for tangent. It only touches the curve at the point P, nowhere else. What do I need to make a slope? Yesterday and Wednesday, what do I need to come up with a slope for a line? Y'all wrote it down. I saw you writing stuff yesterday and Wednesday. What do we do to get a slope? And how do we find that m? That was the y equals mx plus b was the equation in which we used m. But how did I get m? Aha. And to do rise over run, I needed 2 points, yes? I only have one at the moment. This is my problem. This is the problem calculus was developed to try and overcome. I only have told you I have 1 point. Where do I get the other one? So let's actually do a practical example. Instead of just making this arbitrary and anything, let's pick a particular point on a particular curve. I am going to use x squared. Again, yesterday, we talked about this curve. What's this graph look like? Our parabola. Great. Graph it. Grab your graphing calculators, draw yourself a picture, get on Desmos, however you want to do it, draw a picture. And somebody give me an x value other than 0. And we'll use that as the x value for our point. Somebody pick an x. I heard it cry from the back. 2. So if I'm at 2, the point on my curve, P, will be the point 2, 4. The line I'm looking for only touches the curve at the point P. But in order to get the slope, I need rise and run. I need a second point. So what I'm going to suggest to us is that we pick some other point on the graph. Any other point you want. I'll make my life easy to start with. Let's use the origin, 0, 0. Now I've just pulled this point out of my ear, thin air, made it up. But now I have 2 points. Let's build the slope between P and Q. And I'm going to call that slope MPQ. Now Q is over here to the left of P. So my slope should be a positive number because as we go from left to right, we are rising. What is this slope? Rise over run, change in Y over change in X. Perfect. Which means you can give me the equation for a line that has this slope and goes through our point P. The line that goes between these 2 points, I'm going to use, instead of mx plus b, I'm going to use the point slope version. The point slope version y minus y0 equals mx minus x0. I'll use the point P for my x0 and my y0. So I have y minus 4 equals slope x minus 2. So far, so good? I want to put my calculator under the screen and show you, but my batteries just gave up the ghost. Therefore, we get out the spare batteries. Here's our parabola. I'm going to change the window a little. I really don't care about negative y values all that much. And I'm really only concerning myself with x values that are close to 2. So I'm really only going to look at this half of our parabola. Please notice, there is our point P, where x is equal to 2. Now, I'm going to put in this equation. In order for me to put in this equation, I have to have y all alone. So I'm going to add the 4 to the other side. And then I'm going to type it in just like that. Now I can't see it over there. I'll put it over here. And we see the line exactly the way we predicted it would go, cutting through the point 0, 0 and through our point P, 2, 4. So far, so good? Yes, sir. I don't have to, but if I wanted to get it as mx plus b, I could, right? I could multiply this out and simplify it, and I would get y equals 2x. But I want to leave it this way for a reason that will become obvious as I move on. Okay? So this line doesn't actually work as a tangent line because this line goes through 2 points on our graph. And I want a line that only goes through 1 point on our graph. This line cuts a piece of the graph away by going through it twice, right? There's a little bit cut off on the bottom. Cut. Talked about this yesterday. We talked about trig functions. The names of the trig functions are weird. Secant, secare means to cut. We're going to call this a secant line. Now, the problem with this secant line, as I said, it goes through 2 points. And I pulled 0, 0 out of thin air. So let's pick a different Q. But let's not pick a different Q arbitrarily. Let's pick a Q that's closer to P. What happens if I do this again, but I move Q closer? So I want to move the X value closer to 2. Okay, well, let's cut the distance in half. Now I'll use this point. Do it again. Find the slope, and let's write the equation for our line. What motion did you just make with your hand? You pivoted it, right? And if we think about what's happening, we've moved this bottom point further up, right? So what's going to happen to our line's angle, our slope? It's going to get steeper. As a matter of fact, the slope in this case is bigger, a steeper line. And then the 4 and the 2 are the point P. They didn't change. The only thing that changed is our slope. So I can actually write this equation the same way. Jordan, this is why I didn't, I'm sorry, not Jordan. I'm screwing up your name. Say again? Sign. The reason I left the line like that is to see the consistency. The only thing that changed in this was the slope. If I graph this one on top of everything else I've graphed, well, then I see, here's my new line. It is steeper. Let me get rid of the old line. There's our parabola. Here's the line that goes through one. Oh, it cut off a much smaller section, didn't it? As a matter of fact, these 2 points are a lot closer together, and we're going to cut off a smaller piece. Okay. What if I get closer still? Let's move in closer. I'll cut the distance in half again. Now I need to ask you a question. What's the y value for that point? Say again? 9/4. I take 1.5 and I square it, because that's our equation, right? X squared. 9/4 is 2.25. I'll use it in decimal for the moment. 2.25. And now I can do the same thing. 4 minus 2.25 over 2 minus 1.5 is 1.75 over 0.5, which is 3.5. My slope got bigger still. All right, let me get really close. 1.9. What's my y value this time? Four minus 3.61 over over 2 minus 1.9 is 0.39 over 0.1, or 3.9. I could get even closer, couldn't I? I could do 1.99, 1.999, right? Let's do one more. Let's do 1.99. My y value is? So 4 minus 3.9601 over 2 minus 1.99. The bottom is 0.01. The top is 5. I get the 0.0399 part. Wait a minute, if I do that division, I get 3.99. Okay. Okay. I got a sneaking suspicion here. Look at these equations for our secant line. As our Q point gets closer and closer and closer to our our P point, our slopes seem to be closing in on some number. What number do you think they are approaching? If they're approaching 4, will they ever actually get there? I don't think so. I think I'm going to keep getting more and more 9s as I get closer and closer and closer, but I don't think I'll actually get to 4. But what if we look at what happens with our line having a slope of 4? I'm going to think that this idea is the right one. I should be closing in on the number 4. And if I'm closing in on the number 4, then I think the slope of our tangent line should be 4. Let's take a look at what happens if I go back into the equation of our line and I replace that 2 with a 4. Oh, do you see a piece that we cut off? It doesn't look like we cut off anything. Let's look closer. On the calculator, right here, there's a zoom button. I'm going to hit zoom, and I'm going to zoom in. And I'm going to zoom in at the point, as close as I can make it, where x equals 2. Really close to 4. There's my parabola. There's my straight line. You see how it's ever so slightly different? But right there, does it look like it's cutting anything off? If I have this curve that's bending upward, this line, if it only touches at one spot, shouldn't cut anything off at all. Wow. I think that's correct. I think that's our slope for our tangent line, and then the equation of our tangent line and now I can write it in mx plus b form if you want. And have the equation for my tangent line. Questions?
We make it like how we did basically 5, or did we like test test out graphs first and then decide like what window we should try it on.
I don't particularly care about what window we try it on first. I would actually say I want to know mostly what the original graph looks like, y equals x squared. And then I want to make sure my point is somewhere in that window so I can kind of visualize what's going on. The actual physical graph isn't always going to be helpful to me, especially when I look up close and I can barely tell these two pieces apart. So that idea matters. But what matters to me, I think, a little more is this picture where I see there's my curve and there's this line that just grazes it. That is truly only touching once. I will admit I have a bias here. I'm not sure we've done enough. I think we made a subtle but important decision way back at the beginning of this. I picked my point Q to the left of me. What happens if instead of using that point with Q on the left, I have that point with Q on the right? Oh, crap. If everything is nice enough, there's a really technical mathematical definition of what nice enough means in this case. I'm not worried about that right now. If everything is nice enough, it should work the same. Underline that word. Should. Trust, but verify. Let's check. So I want to pick, and I want to do the same process now with Q values where the X is bigger than 2. So let's go back and try this one more time. I really don't even need to write the equation of the line. I just need to write the slopes. And we'll use values that are bigger. Than 2. But again, we'll close in on 2 the same way. I would like 4 slopes from you. 4 y values, 4 slopes. I gave you 1 y value. Give me the others. If you have the graph of our parabola on your calculator, instead of retyping, you can use the trace button and put in the X value you want, and it will spit out the Y value. All you have to do is hit that trace first. And then you simply type in X values. It sure looks like from these calculations, I am getting the same answer, whether I let Q come from the left towards P or Q come from the right towards P. The fact that these agree means I'm pretty sure I got it right, that the correct slope for my tangent line is 4. Questions? The downside. My notes actually didn't use the 0.24. My notes used the 0.11. What if I want to do this for the 0.11 instead? I got to do this whole thing all over again. I think I gotta hit myself upside the head with the text. This does not sound like a fun time. So while this is giving me a correct answer, regardless of what point I pick, this doesn't seem to be a very easy process. It seems very tedious. At the moment, yes, it is tedious. I'd like to make it better and faster, but this works. As a matter of fact, it works almost every time. What do you mean almost? Well, there are some particular exceptions we'll run into as we try and make this idea a little more formal. But let me ask this question. I pulled these numbers out of thin air. What if I hadn't? What if I said, I'm going to tell you that the point Q has an arbitrary X value, as long as that X is not 2. Well, if that's the case, what's my Y value? X is not 2. It's just, the X value is just X. What expression should go there for the equation we're working with? But our f of x is something we know. What's f of x in this case? Aha! Now, let's write the slope between P and Q. Remember, P is right up there. P is 2, 4. So I take the y value minus the y value. And the x value minus the x value. And now we see the problem I'm talking about. If I were to actually take 2 and plug it in here, what's the bottom of this fraction? And what happens when you divide by 0? Your calculator tells you to go yourself. You can't divide by 0. It's mathematically inconsistent. It doesn't make sense. Okay. The fact that the bottom of this would be 0 if I put in 2 is a problem. But I wasn't putting in 2. I was putting in numbers that were close to 2, but not actually 2. If I take 2 and I put it at the bottom, I get 0. What if I put it in the top?
0 on top.
Oh. Okay, wait a second. Dividing by 0 doesn't make sense. What's 0 over 5? What's 0 over 3? What's 0 over 0.1? When I have a 0 on top, I should get 0. When I have a 0 on bottom, I don't know what to do. We're going to call this idea an indeterminate form. I don't have enough room there. I'll write it down here. And one of the goals of calculus, one of the goals of analysis, the theory of calculus in general, is to try and figure out when things are indeterminate, how can I determine that? I want to figure out what to do with this to make it into something I can actually evaluate. But this idea needs to be chewed on and beat on a little more. I need to get some more details in here. I need to be a little more of a pain in the ass. But before I do that, anybody drive to campus today other than me? Okay, good. When I started, I wrote down tangents and velocity problems. What's that to do with velocity? I live roughly 20 miles from here. It took me about 40 minutes to get here this morning. How fast was I going? Where did 30 come from? Say again?
If it was at the 20 minutes, we're going 60.
And it's going to be twice that long, so I go half as fast, right? But I can also do the formal calculation. Velocity, well, speed, is distance traveled over elapsed time. So I'm going to convert 40 minutes to hours. I'm going to say that's 2/3 of an hour. And then I will say that my speed was 20 miles divided by 2/3 hours, or 30 miles per hour. Absolutely. However, I'm pretty sure I did not back out of my garage at 30 miles an hour. I did not weave through my neighborhood at 30 miles an hour, and I sure as hell didn't do 30 miles an hour on the parkway to come out Route 22, to come down 66. I didn't do 30 miles an hour coming up the hill, did I? I shouldn't have. So this was not my speed the whole time. This is an average. As a matter of fact, if I had started my stopwatch when I left my house, I could call that time 0 and distance 0. And I stopped the stopwatch when I parked in the parking lot at time 2/3 hours and distance 20 miles, then this calculation would actually look like this. Hey, wait a minute. That's a slope. But it's a slope on a graph whose axes are time in hours and distance in miles. And I have the point where I started in my garage. And I have the point where I finished on campus. And this calculation is the slope of the line connecting those 2 points. I need you to take out your phones, point your cameras up here. I want you to take a picture of that in the air. Ready? Here we go. Take a picture. You get it? Look at the picture. Is it moving? Clearly it didn't stop moving, did it? So what the? How does your picture not show this object in motion when it clearly didn't stop moving? I am driving here this morning. I have a speedometer in my car. What does your speedometer tell you? How fast I'm going right now. Not an average. It's measuring now, at an instant. If I think about what's really happening, I can think about what you just did with your camera. You took a picture. How does a camera work? That's what a camera does. But how does the camera actually work to do that? Okay, when you push your button on your phone, some of you, if you didn't have your sound turned off, would have heard something. What would you have heard? That click. What is that click? That click is a holdover artifact from mechanical cameras. When you click the button on a camera, it opens a shutter, an iris, and lets light in, and then it closes it really fast. Now on the camera on your phone, at the back of that, behind the shutter, is a little array of pixels, however many megapixels your camera is, how many millions of dots. Each of those little dots senses how much light is on it. And it tells you what color of light is on it as well. But it does it only while the light is there, only while the shutter is open, which is a very, very small amount of time, isn't it? that click was open, close. If I think of these numbers that we were looking at here as intervals of time, then what I've really done is I've said I want the amount of time I am looking at to get smaller and smaller and smaller. The object wasn't not moving. It was that the amount of time your shutter was open was not enough for it to show movement, right? If I look down at my speedometer, it tells me how fast I'm going. Do I stop? The ball didn't stop either. It has a velocity. In the picture you took, this ball is moving. It just moved such a small distance that we couldn't see it move. The amount of movement in our graph was so small that the piece we cut off was so tiny that we didn't see the motion. Figuring out how fast something is going is exactly the same calculation as figuring out the slope of that tangent line. If I take this object and I drop it, the only thing that affected is what force? Gravity. And last time I checked, the position of an object, the distance it travels under gravity, is given by this equation, where we start at a distance of 0 and measure distance traveled, so down is a positive direction. If I want to know how fast this object is falling at time 1, I could ask, how far did it travel over what period of time? So I could say, oh, well, at time 1, we will be at the position 4.9 meters below where we started. I stick my hand out the window, I let it go. 1 second later, it is 4.9 meters down. Doesn't tell me how fast it's moving, just tells me where it is. So pick a time, either right before 1 or right after 1, that's just a little bit away from 1. And then let's let that time get smaller and smaller and smaller. And what I would really be doing is I would be using the point 1, 4.9 and another point that's just a little bit different than 1, say 1.1. 4.9 times 1.1 squared is 5.929. And I could figure out how far we went, right? And then I could figure out how fast we were going. I could then get a smaller time interval. I could use times that were before 1, right? And if I could figure it out using the same setup we just did for slope, I could tell you that this object was falling at 9.8 meters per second. Make the table and see what your numbers get closer and closer to. It's the same setup. And that's the key piece of insight here, that this same kind of problem shows up in so many different situations. So now if I can figure out how to do this without making an 8-mile table over and over and over and calculating all this crap, I'll be better off. And that is where we will start algebraically on Monday. Remember, in case of bad weather, I will try and teach from home, provided I have power. Be on the lookout for announcements, because they don't know if we're getting, I don't know, an inch of snow or 3 million miles of it. Nobody's figured that out yet. I hope to see you all on Monday.